Hey gang, welcome to Computer Graphics. We're going to be doing things just a little bit differently today because due to weather, we're going to, I'm going to have one of the students, Eric Pitts, is going to share his screen and he'll have the notes up there that we can talk our way through. Okay, so Eric, if you don't mind bringing your screen up. Awesome. And we need to be on page 31 of the notes.
Okay, there it goes.
Okay. Okay, thanks, Eric. I appreciate that. Although it looks like it may be recording your video rather than mine, so maybe you want to kill your cam. I'm not 100% sure if it's going to show your video or if it's going to just show the notes. Okay, well, we'll find out when we look at the recording, okay? Because you might be staring at Eric's face through the recording, or maybe you'll be seeing mine, or maybe you'll be seeing the notes. I don't know. It'll be a surprise, and we'll have to see. Okay, so what we're going to do today is we're going to do two things. We're going to go over another example of computing a composite matrix. You'll remember last time we introduced the idea of composite matrices. We actually introduced the idea of matrices, of using matrix notation itself rather than just equations. And the reason why we said we're doing this is so that we'll be able to have improved efficiency. We'll be able to do things faster. So we're going to do one more example. And then the second part of the class is going to deal with background on really on vectors and basic linear algebra, dot products and cross products. You've probably seen all of that, but because it's so critical to sort of the next phase that we're going to be looking at, I wanted to take the time to make sure that we had covered that in the notes. So that's what we'll do. We'll do another composite matrix, and we will also do sort of some background on vectors and vector operations. Okay, so we're on page 31, section 2.2.2. And what we're going to do here is we're going to look at a problem where we're trying to have some sort of a arbitrary line in space, a line segment with a start with a start point and an end point, and those points will form a line segment, and we want to rotate something, some object. It doesn't matter, a point or lots of points, vertices of polygons. We want to rotate those points through some angle, but instead of doing it around one of the major axes like we've done in the past, we want to rotate around that line in space. You might think, well, why would I want to do something like that? Well, think of a sci-fi movie where you have one of those spinning space stations, right? And you're approaching it from some angle, or your camera is at some angle. You'd want to be able to see that, you'd want to be able to rotate that space station in any orientation. So that's something we want to do. By the way, I can hear some people in the background, so if you'll check and make sure that your mic is muted, that would be really great. I appreciate that. Thank you. Okay, so given a line segment in 3D space defined by P1, which of course will have an X, Y, and Z component, and P2, which obviously will also have an X, Y, Z component, we want to define a composite matrix. So we want to build a composite matrix that'll allow us to do an in-place counterclockwise rotation through some angle, call it phi, with respect to that reference line P1, P2. And we're saying it's a counterclockwise rotation. Well, it's counterclockwise if you're at P1 looking down the line segment towards P2. So that's what we're going to be doing there. Okay, so it's actually going to end up being a 7-step process. So the first thing we'll have to do is we'll have to take the point P1 and move it to the origin. Then we're going to take our reference line and we're going to rotate it into the XZ plane. Okay. And that's going to be accomplished by an x-axis rotation. And then we're going to take that reference line that's now in the XZ plane and we're going to rotate it so that that reference line lines up with the z-axis. And then we can do a z-axis rotation that we've already defined, a counterclockwise z-axis rotation of whatever points we want. And then we undo the steps that we've done so far. We will reverse the effect of step 3. So in other words, we'll move the line, back away from where it was lined up with the origin, back to its position in the XZ plane. That's step 5. And then we'll undo step 2, which means we will do an x-axis rotation that'll get the line back at its original angle. And then the last thing we will do is we will undo step 1, which will put the P1 point back to its original position. So we're going to be doing 7 steps. Now, instead of doing them 7 steps separately, we're going to compute a composite matrix. So really we can do all 7 of these things at once. That's the whole point of what we're doing here, is we're trying to build a composite matrix that will allow us to do all of these operations together. So if we scroll down to page 32 and we look at the step 1, you can see that I've got a line segment that goes from 335, that's where P1 is, to 6.57, that's where P2 is. And so the first step is we want to move that line segment from where it is, drawn in solid blue. We want to move it so that point P1 is at the origin. So the point 335, we want to move that to 0, 0, 0. And when we do that, if we move both endpoints, we will get the dashed line segment that I have drawn there as P1 prime to P2 prime. Okay, so P1 prime is 0, 0, 0, and P2 prime is 3.52. Now, how do I get that? Well, I use a translation matrix, right, that I've gotten there. So if you want to move something from P1, if you want to move P1 to the origin, well, along the bottom row, right, it's -3, -3, -5. And if you do that, and then you multiply your points, if you multiply 335 times that matrix, you get 0, 0, 0. And if you multiply 6.57, you get 3.52. And you can see that over in the little table off to the right. So that's step 1. Okay, so scroll down just a little bit more and we can look at step 2. In step 2, now that we've got our line segment from P1 prime to P2 prime, we want to rotate that line segment into the XZ plane. So the position it's currently at is on the left, and we want to rotate it so that that line will be on the right. Now, before we get into the formulas and the math and all that, let's look at and think our way through this line segment and what's going to happen if we rotate that line P1 prime, P2 prime through the angle alpha into the XZ plane. Well, if you look at the line that goes from 0, 0, 0 to 3.52, right, we can break it out into its X, Y, and Z components, and we can give those components their own name. So X is going to be 3. The X distance is 3, and we'll call that A. So you see where I have there A equals 3? Well, that's the distance along the X-axis, I guess you could say, to get to 3.52. That's the X component. And then the Y component, that's the vertical component, right? That we'll call that B, and that's 3.5. And then the Z component, that's the distance component, we're going to call that C, and it's 2. So A is the X component, it's 3. B is the Y component, it's 3.5, and C is the Z component, and that's 2. And so I've drawn those little dashed lines there to let you see, to break out each of those components. Okay. Now, if you look, you can see that we actually have a couple of triangles. We've got a triangle that involves our line segment from P1 prime to P2 prime. If in that triangle, that's the hypotenuse, you see that we've got the other components of that, we've got the X, the A part, and then we've got this thing called S. What is S? S is the shadow of our line segment onto the onto the YZ plane. So if you had a light that was shining directly from plus X, so the light source is in plus X and it's shining, it's far, far away, so all the rays are parallel. It's shining towards our line segment, P1 prime to P2 prime. That line segment will cast a shadow on the YZ plane, and that shadow is is S. That shadow is S. Okay, so if you think about that shadow S, it's going to have a length. What is that length? Well, we can calculate it because we can see that we know to get the length of S, we need B and we need C, because C is the distance in Z, that's 2, and B is the distance in Y, that's 3.5. And so S would be the hypotenuse of that triangle. So if you took C squared plus B squared, and then you took the square root of that, that would give you the length of S, right? C squared plus B squared, take the sum them together, take the square root of that, that'll give you S. And you can see that I have that written there at the bottom. Since C squared plus B squared equals S squared, S is the square root of C squared plus B squared. So then S will be, if you do the math, 2 squared is 4. Well, I've been calling B 3.5, but really if you want the math to work out, it needs to be, you know, something more like 3.4641, and then there's a bunch of crap. But basically, I'm trying to get a number that when I square it, I'll get 12. So it's not exactly 3.5 squared is not exactly 12, but 3.4641, blah, blah, blah. The square of that'll give you 12. And why am I trying to do that? Because I'm trying to come up with something that when you take 4 plus 12, you get 16. The square root of that's 4. So that B vertical distance that I'm showing is 3.5 would actually, for the math to work out, would actually need to be something like I said, 3.4641, and then blah, 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 blah. It just keeps going. It's an irrational number. Okay. But I'm trying to make my math work out easy. Okay, so now that we know that S is 4, right, I can get the length, which I'm calling L, of our P1 prime to P2 prime, because now I have a triangle where S is 4 and A is 3. So if you take A squared plus S squared, that's going to give you L squared, right? And so L is the square root of A squared plus S squared. A is 3, S is 4, 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, the square root of 25 is 5. So that gives us a beautiful little 3 by 4 by 5 triangle, okay? Well, that's great because, but you might say, well, Mike, you did some math there and you drew some pretty triangles, and now I understand the relationship here. I understand that the length of P1 prime to P2 prime is 5, but how is that going to help me rotate that line segment into the XZ plane? Well, if you scroll a little bit to the top of the next page, right, you'll see that, well, what do we want to do? If we want to rotate do an x-axis rotation through the angle alpha, we don't really need to know alpha. We need the sine of alpha and the cosine of alpha. Well, the sine of the angle is the opposite over the hypotenuse, and the cosine of the angle is the adjacent over the hypotenuse. So if you're looking back at that little triangle, the opposite is B, the hypotenuse is S. So you've got 3.5 over 4. Again, it's not exactly 3.5. But anyway, you do that division and you come up with 0.866. The cosine of that angle alpha is the adjacent over the hypotenuse. That's C over S. C is 2, S is 4, 2/4 is 1/2, 0.5. So that gives us, now that we have the sine and the cosine, we can plug those into our x-axis rotation matrix, right? And that gives us the numbers that we need to be able to rotate that angle, that line segment into the XZ plane. So you pump in 0.000 into this matrix, and of course, it's still going to come out as 000. You pump 3.52 into this matrix, or multiply that point times this matrix, and you'll get 304. Now let's scroll back up again to the bottom of the previous page, and you can see that the number 304 makes sense, because when we rotated P1 prime, P2 prime into the XZ plane, that whole little triangle with its shadow has to rotate into the plane. And what was S? S was, the length in Z, the displacement in Z of that line. And so it's got to have a length of 4. And since we're going into the XZ plane, our Y value is 0. Our X value hasn't changed, it's still 3. So that's why it's 304. The X value 3 didn't change from the drawing on the left to the drawing on the right. We rotated into the XZ plane, which means our Y is 0. That's why the second value there is 0. And the Z value has to be 4, right? Because that's the length of our shadow, and that little 3x4x5 triangle has to be preserved. And the only way that can happen is for P2, and we're calling it double prime now, is at 304. Okay, scroll back to the down back so that we can now look at the math. You can see I do the little matrix multiplication there. So that if it's been a while since you've looked at matrix multiplications, I went through in detail every single calculation, so you can see how 3.5, well, again, 3.4641, 3.52, how that gets converted to 304. Okay, now on to step 3. Well, now we have the triangle, our little 345 triangle that's in the XZ plane. We need to rotate it counterclockwise from plus X towards plus Z. So we need to rotate that through that angle beta there. And what we're going to try to do, or what we're going to do, is we're going to line up our line segment now with the Z-axis. So you can see on the right what's going to happen there. And it's pretty easy to see that we're going to end up with 005 as 0.2 triple prime, because 5 is the length of the line segment from P1 prime to P2 prime. So when I rotate that line, right, to match with Z, it's got to be 005, because the length of the line segment's 5, and doing the rotation's not going to change its length. Okay? Again, we don't really need to know the angle beta. All we need to know is its sine and cosine. We've got the little triangle, so we can look at the opposite over the hypotenuse, which will give us the sine. That's A over L. That's 3 over 5. That's 0.6. The cosine of that angle beta is the adjacent over the hypotenuse. The adjacent is S. The hypotenuse is L. S is 4, L is 5, 4/5 gives us 0.8. We plug that into our Y rotation matrix, and we can plug the points through, and we get, as you would expect, 304 becomes 005. Now note I have some things here in red. I'm doing that to draw your attention to the fact that if you look at our Y-axis rotation matrix, okay, you will see that I swapped the sign of the signs. And remember our lecture from Wednesday of last week when I talked about that? I said, well, if you flip where the sign is, right, what that's going to do is that's going to reverse your rotation. If you go back and you look at the way we defined Y-axis rotation, you will see that we defined it from plus Z to plus X, but we're going from plus X to plus Z, right? So we're going in the opposite direction of the way we defined it. So I've got to flip my signs there. So that's why if you're carefully following through the notes and you go back and you look, you'll see that I've got the signs swapped. Well, that's because I'm doing a rotation that's in the opposite direction of the way I originally defined it. And we spent a lot of time on Wednesday talking about that and me breaking it down. It is important that you not just say, oh, here's the matrix, let me plug it in, right? That you understand what the matrix is doing and the direction of rotation that it's defined in, because sometimes if you're doing like what we're doing here, you might need to reverse it, because maybe for your particular problem, you need to rotate it in a direction that we didn't originally define it in. Okay. Any questions about that? You'll need to speak up verbally because I can't see chat. Any questions? Okay, well, we're through the hard parts now. The rest of this is going to be pretty straightforward. If we look at step 4 is just our rotation matrix, counterclockwise, standard Z-axis rotation. I don't know what angle I wanted to rotate my points through, so I don't break it down any further than just, our normal cosine phi, sine phi, little Z-axis rotation matrix. But whatever that would be, we would work out those values, and that would become our R sub Z, our rotate sub Z matrix. Okay, so now we're halfway through the process. We've done our rotations, and we've got to put everything back the way it was originally. So we've got to, in step 5, reverse step 3. There are really no more calculations to be done for the matrix. You just basically, we had the sine and the cosine, 0.8 and 0.6. All we're going to do is we're going to swap the sign of the signs, right? And that's why I have those in green to show you that they're changing, because I just want to undo the rotation, the Y-axis rotation that got me to where I'm at. So I undo that. So 0.5 goes back to being 304. Okay. And now in step 6, if I can scroll down there, in step 6, I do the same thing. I reverse the effect of step 2. So again, I swap the sign of the signs and use the same numbers that I had to do the x-axis rotation. So 0.5 and 0.866. If you plug 0.304 into that, that'll put that back to 0.3, 3.52. So I've reversed that. And then the very last step is I've got to move everything back to that little line segment back to where it was originally. So 335 is what I'm going to be translating by. Again, those were negatives in step 1, so they're positives in step 7. And that gets my 0.000 back to 335 and gets 3.52 back to 6.77. And so that's all the calculations. I've defined for you all 7 of the matrices. Now, why did I do that? I did that so that if you look on the top of the next page, 35, I want to compute a composite matrix that's all 7 of those matrices multiplied together. So the first translation, which is T minus P1 times the rotation in X times the rotation in Y times the rotation in Z times the rotation in minus Y times the rotation in minus X times the translate in plus P1. So that's the whole little pipeline there. So what I can do is I can multiply all those together. And once I do that, I now have one matrix. So if I have a 1,000 vertex object that I'm trying to rotate, originally, without a composite matrix, I would have had to have taken all 1,000 of those points and multiplied them each in turn sequentially. So all 1,000 points times the first matrix, and then the result of that, all 1,000 points times the second matrix, and then the result of that, all 1,000 of those points times the third matrix, all the way through that pipeline. But if we multiply all those matrices together, I don't have to do 7,000 matrix operations. I only have to do 1,000 matrix operations. Each point can be multiplied by this composite matrix, and it'll do all 7 of those operations together at once in parallel. So even if I don't have any kind of graphics hardware, it still makes sense to compute a composite matrix and do these operations on a composite matrix, because you'll do 1/7 of the work. That's a big savings. If I can take what it costs and cut it down by a factor of 7, that's a huge savings, right? Instead of 70 minutes, instead of an hour and 10 minutes, it would take me 10 minutes to do an operation. That's a huge savings. 10 minutes versus an hour and 10 minutes, right? So that's great. Now, if you've got graphics hardware, you can do far, far better. If we had enough graphics hardware, in fact, we could do all 1,000 of those point computations times the matrix in a single step, right? So you don't have to do 1,000. Well, you do have to do 1,000 point multiplications. But if I had enough hardware, I could have 1,000 copies of my composite matrix, and I could run 1 point times each of those, and bam, I could do it in 1 step. That'd be a lot of hardware, obviously, but I'm just showing you, if you had enough hardware, there's no mathematical reason why you can't do all the calculations in parallel. You could. And then think about what a matrix calculation itself is doing. You can multiply all of the rows times all of the columns simultaneously. So that gives you a huge speed up too. So it's not like doing so even doing a single matrix multiplication is faster than doing the X calculation, then the Y calculation, then the Z calculation. So that speeds things up. Now, you might have noticed, you might say, well, like, that's great, but I still have to pay a little bit of a cost, don't I? It's going to take me 7 steps to do that matrix, to compute my composite matrix. So, you know, even if I had infinite hardware, isn't it going to take me at least 8 steps, 7 steps to build the composite matrix, and then 1 step to multiply the points times that composite matrix? So isn't that the theoretical best I could ever do given infinite hardware? To which I say, no, you can do better than that, because matrices, you don't have to go through this 7-step multiplication sequentially. You could multiply the first 2 matrices together, and at the same time be multiplying the second 2 matrices together, and at the same time be multiplying the matrix 5 and 6 together. And you can see that where I have there in the middle of the page, I have step 1, 3 parallel matrix multiplications. So your composite matrix could be, it's still the same equation, but I'm doing the first two, and then the 3 and 4, and then I'm doing 4 and 5. I'm doing those in parallel. And then once I have that, I could take, so now I've got 4 matrices. I could take the first 2, multiply those together. That's what's shown in step 2. And I could take the result of the second 2, or the result of matrix 5 and 6, the result of that multiplication with the last matrix, and I could multiply that together, and that would give me 2 matrices. And then I can multiply those 2 matrices together and get the third one. So it doesn't take 7 steps. I could do it in 3 steps, right? By doing first 3 of the matrix multiplications in parallel, then 2 matrix multiplications in parallel, and then the final matrix multiplication by itself. So really, rather than having, with infinite hardware, rather than having 7,000 timestamps or time steps, I could do the whole problem theoretically in just 4 steps, 4 time steps. That's amazing. Given enough hardware, let me repeat that, I can go from a process that would take me 7,000 steps, right? I can get that down to 4. And actually, remember those 7,000 steps, that's 7,000 matrix multiplications. So if you weren't using matrix multiplications, if you were using equation format, like you're doing in your in your program, you would have to calculate X, Y, and Z separately, sequentially. So really it's 7,000 times 3. So you're taking something that would take 21,000 time steps, and you're getting it down to 4 timestamps, given sufficient hardware. This is why we use composite matrices. This is why we use matrices. It allows us many orders of magnitude increase in processing speed. So you can, instead of doing a handful of polygons like you're doing in your programs, you can do thousands or tens of thousands of polygons with the right hardware. Questions? Any questions about that composite matrix? Why we computed it, how we computed it?
Yes, sir. So not so much about the matrix, but what I was wondering is, where you're saying that it's going down to 4 or 5 steps. What is the overhead for loading 1,000 copies of this matrix into the GPU? I don't know a lot about that sort of hardware. Is that a significant factor?
Well, obviously there would be overhead in that. That's why I'm saying theoretically, right? But much of that can be parallelized with the right hardware, because those operations they in no way sequentially depend on one another. Now, if you're, in hardware, if you're trying to copy things, it would depend on the hardware architecture and all sorts of things that we're not ready to get into here in computer graphics. And I'm not really a hardware guy anyway. But even if there's some overhead associated with that, what I'm trying to show here is an analysis like we would do in 325, or we might, where we try to talk about, okay, what's a lower bound on the number of operations? And we've gone from a lower bound of either 7,000 operations or 21,000 operations, if you're going to think about it in terms of each of those operations involves an X, a Y, and a Z computation. If you're doing it sequentially, that's the minimum, that's the lower bound, right? Where we're moving to a situation where I'm showing you a lower bound in the number of timestamps of 4. Does that mean you're really going to get only 4 timestamps compared to 21,000? I doubt it, because there's going to be some overhead, but that overhead's teeny tiny compared to the speed up you're getting. And remember, 10,000 polygons is really a fairly small number of polygons these days, right? So So no, I'm not promising you that 4 is the upper bound. It's a lower bound, but it gives you an idea of the scale of the savings that you're getting. And that's what I'm trying to do here. But that was a good question. Any other questions about this? Okay, good. All right, so let's proceed forward to the next page, 36. And you can see what we're going to do here is we're beginning to cover some background on linear algebra. And again, many of you have probably taken linear algebra. And even if you haven't taken linear algebra, I know a lot of this stuff is covered in the freshman pre-calculus and calculus series. But I like to run my courses as if I'm not assuming any math more than high school math. So I wanted to present it here. So the first thing we want to do is we want to talk about a vector and the difference between points and vectors. So if you look at the little diagram at the top here, you see a point 2, 1. And we played with these since junior high school at least, right? Where you have the displacement in x, which is 2, and you have the displacement in y, which is 1, and that gives us a point at 2, 1. And we normally write that as an ordered pair, 2, 1, and we put it in parentheses. So that's the point 2, 1. You could also talk about 2, 1 as being a vector, okay? A vector is different from a point in that a vector specifies a direction and a magnitude. A magnitude and a direction. That's what a vector is. Now, you might say to get a magnitude is just another word for length. So to get something with length and direction, don't you need 2 points, Mike? Don't you need a line segment? How can you get that out of just a point like 2, 1? Well, the answer is in vectors, we assume that what you're giving me is an end point, and we assume that the start point is the origin. So in a 2-dimensional system, it's 0, 0. In a 3-dimensional system, it's 0, 0, 0. So it really is a directional line segment, but it's a directional line segment in this case that goes from 0, 0 to 2, 1. And notationally, frequently what we do so that there's a visual clue that I'm talking about a vector rather than a point is you use angle brackets. So when you're talking about 2, 1 as a point, you normally put it in parentheses, in the rounded brackets. If you're talking about 2, 1 as a vector, you put it in angle brackets. And that's just a little quick visual way of telling someone, yeah, I'm giving you a point here, but I'm treating it as a vector, and it's really like a line segment, and the other endpoint, the start point, is the origin. It's all you're doing there, okay? So there's the 2D vector 2, 1. Now, if you scroll to the bottom of the page, you can see that vectors can be represented in these kind of an ordered pair, like 2, 1, or an ordered triple if you're talking about 3 dimensions. It can also be shown as a vector that you could write it as a vertical vector, a little if you've got a 3D point or a vector in 3-dimensional space, you can write it as x1, y1, z1. You can write it vertically or you can write it horizontally. Either way works. Usually it's specified as a column vector. So if you want it to be a row vector, it would be the transpose. And that's why you'll often see a little t as a superscript. That means take that thing and throw it on its side, just rotate it. Doesn't change the values at all. Sometimes we want to do our math with it as a row, and sometimes we want to do our math with it as a column. We're free to do it either way. So scrolling to the top of page 37, we're starting to get into some properties of vectors that, again, you would have studied all of these, but just to remind ourselves, if I've got a scalar is just a number, a non-vector, it's just a normal number. So if I take a scalar and I multiply it times a vector, what that does is it changes the magnitude or the length of the vector. It does not affect its direction in any way. So for example, if I have our little vector here that we've been playing with, 2, 1, and I multiply that vector by 2, the scalar 2 times the vector, I do the multiplication component wise. So I take 2 times 2, that'll give me 4. And I take 2 times 1, that'll give me 2. So multiplying the scalar 2 by the vector 2, 1 gives me the vector 4, 2. And 4, 2, the length of that's going to be exactly twice the length of 2, 1. Okay, so if you take a vector and you multiply it times the scalar, all you're doing is changing the length of that vector. You're not changing its direction in any way. And of course, the opposite of that's true too. You can, you don't have to necessarily be increasing the length of the vector. You could be decreasing the length of the vector. Vectors add and subtract component wise. So if I've got 2 vectors, P and Q, I can add them together by adding them component wise. So I would add px plus qx to get me the x value of the added vector. I would add py pq py qy excuse me, to get the y component of the vector, pz plus qz to give me the z component of the vector. And it doesn't just have to be, 2-dimensional and 3-dimensional. It works for any dimensional vector. So this works for an n-dimensional vector. But let's give a concrete example here, okay? So p is the vector from that is the vector 3, 3. In other words, from 0, 0 to 3, 3 defines the line segment P, which is just another word for the vector P, right? So 3, 3 defines the vector P. 2, 0 defines the vector Q. And you can see I have it drawn on the X line segment right there at the bottom. You might say, well, how could I add P and Q together to get P plus Q? Because the Q is at the bottom, right? And that doesn't form a triangle. Well, vectors specify direction and magnitude. So you think of them as little arrows. You can move the start point of those little arrows anywhere you want to, okay? So we could take the Q vector, right? And we can imagine instead of 0, 0 being its starting point, let 3, 3 be its starting point. And then the addition of P and Q makes sense because you can see basically what we're doing is we're going to the tip of P and then we're starting there, we're going 2 over in X, right? And that gets us to the point 5, 3. Well, that gives us the vector 5, 3, which is P plus Q. So we do have a triangle. It's just as if that little Q is moving in space from a start point at 0, 0 to its start point at 3, 3. So if the start point of the vector that ends at 2, 0, if the start point changes from 0, 0 to 3, 3, that means the end point will be at 5, 3. See how that works? So that's why graphically it makes sense that you can add or subtract vectors component-wise. At the bottom of the page, we have some properties of vectors and scalars. So there's a commutative property of vector addition. So P plus Q gives you the same result as Q plus P. There's an associative property of vector addition. P plus Q, do that operation, and then add in R. Well, that'll give you the same result as if you had added P plus R and then added that, or sorry, if you had added Q plus R, and then you took that result and added it to P. Same thing. So it doesn't matter the order in which you add together the P, the Q, and the R. Now let me change that. The order matters. If you've got two pluses to do, two additions, it doesn't matter whether you do the first addition and then the second addition, or whether you do the second addition and then do the first addition. So that's the associative property. And you can look at scalars versus vector multiplication. So if I have a plus b, and remember those are numbers like 2 and 5 and 7, things like that. If I multiplied those together and then took that resulting scalar and multiplied it times the vector p, I would get exactly the same result as if I took the quantity b, multiplied that times the vector p, and then took the result of that and multiplied a times it. So again, that's associative. There's a distributive property. If you've got the vector p plus q and you're going to multiply a times that, well, I could multiply a times p and then add in a times q. Distributive property of a scalar times vector addition. Or if you wanted to add the scalars a plus b and then take the result of that, the quantity there, and multiply it times p, you'd get exactly the same result as if you multiplied a times the vector p and then added to that b times the vector p. So that'll give you exactly the same thing. I don't know where that 3 came from there. That's called a typo that just creeps in from nowhere. It's gone in my version and it'll be gone in yours next time you look. Okay. Any questions about those so far? It's just basic stuff that you will have seen again in your pre-calculus class probably. Moving on to the top of page 18, computing the magnitude of the vector. This is basic trig, right, with the Pythagorean theorem and our little triangles. Basically, if you look at, notationally, if you want to talk about the magnitude or the length of a vector v, we write that as double bars on both sides of the vector. And that's our way of writing the length of v or the magnitude of v. And you calculate it as the square root of the sum of the squares of the components, right? So if you've got a two-dimensional vector, v, its magnitude, the magnitude of v is the square root of vx squared plus vy squared. If you've got a three-dimensional vector, its magnitude is the square root of x squared plus y squared plus z squared. Right, and again, all of this comes back to the Pythagorean theorem. For a two-dimensional case, it's just a single triangle, which you see there in blue. If we scroll down towards the bottom of the page, for the three-dimensional version, it's two triangles, but that ought to look really familiar because it's the same 3x4x5 triangle that we were looking at when we were doing our rotations. And I run through the math there, but essentially it's the length of a three-dimensional vector is take your x component, square it, take your y component, square it, take your z component, square it, add those three things together, then take the square root of it. And that'll give you the magnitude, the length. Now, top of the next page, unit vectors. Why do we compute length? We compute length to get rid of it. essentially. Many times we will be working with what are called unit vectors. Unit vectors are vectors with a magnitude with a length of 1. And so a lot of times you're only interested in direction and you're not interested in magnitude. And so if that's the case, you compute a vector, maybe we've gotten a vector v, and we want to normalize it. We want to turn it into a unit vector. So what you do is you calculate the length of v, the magnitude of v, and then you divide each of the components by that magnitude, and that'll give you a unit vector. So let's say that we had the vector 3, 4, okay? And we want to normalize it. We want to turn it into a vector with exactly the same direction, but a length of only 1. Well, how would we do that? Well, first we need to compute the magnitude of the vector, and we've already done that. 3 squared plus 4 squared is 9 plus 16. That's 25. Take the square root of 25, that gives you 5. So that's the length of the vector 3, 4. So the line segment from 0, 0 to 3, 4 will have a length of 5. If you take 3 and divide by 5, that'll give you 0.6. You take 4 and divide by 5, that'll give you 0.8. So the normalized version of the vector 3, 4 is the vector 0.6, 0.8. Okay? Again, sometimes some of the calculations that we're going to be doing later on are going to require that the vector be normalized before you do the calculation. So we're just showing you how to do that calculation now. Bottom of the page, some more basic properties of vector magnitudes. Well, these make sense if you think about it. The magnitude of vector p is greater than or equal to 0. Why is that? Well, a line segment can't have negative length. What's the shortest line segment you can have? Well, the shortest line segment you can have is a point, right? Where the start and the end point are the same. So if you've got a vector that's, 0, 0, 0, both the start and the end point are the origin. So in that case, the magnitude is 0. Any other value where either the x, the y, or the z, or any combination of them are not 0, then you'll have a vector with positive length. It is impossible to have a vector with negative length. It doesn't even make any sense. You can't drive negative 5 miles to work. You can drive 5 miles to work, 2 miles to work. If I'm at home right now, I drove 0 miles to work, but I can't drive minus 5 miles to work. So vectors, the magnitude is greater than or equal to 0. The only time the magnitude of a vector, that's what B is saying here, the vector P, its magnitude is equal to 0 if and only if P is the origin, right? The magnitude of a vector A times the magnitude of a vector composed of the scalar A times the vector P will be exactly the same as if you took the absolute value of A and you multiplied it times the magnitude of the vector P. And I do a little calculation to show you that that is true. The reason for the absolute value on the scalar is, again, you can't have negative length. You can't have negative length vectors. And then finally, D, the magnitude of the vector P plus Q has to be less than or equal to the magnitude of P plus the magnitude of Q. And this gets back to, what you learned again in junior high or freshman geometry, right? The shortest distance between 2 points is a straight line. So if I had a vector P and I had a vector Q and I add them together, I get a vector P plus Q. We normally think of P plus Q as being longer than, greater than the magnitude of P and the magnitude of Q. It could be equal, but that'll only be the case if P and Q both point in exactly the same direction. So you could add P and Q together if they point in exactly the same direction. And in that case, and in only that case, P plus Q would be equal to the magnitude of P plus Q would be equal to the magnitude of P plus the magnitude of Q. Does that make sense? Okay. So with all of that background, that gets us to the two important operations on vectors that we need to know about. We need to know about dot product and cross product. These are sort of why we talk about vectors so much. A dot product of two vectors provides for you, it generates a scalar, it generates a number. So the dot product of two vectors generates a scalar, generates a number, not another vector. But this number that you get from the dot product of two vectors is a measure, provides an indication of the difference between the directions in which the two vectors point. It gives you an indication of the angle between those two vectors. Okay. Why is that going to be important? It's going to be important for a bunch of different calculations. When we start talking about lighting, it's going to be critical. When we start talking about polygon visibility, it's going to be critical. So dot products are our friend. If we want to look at how you compute the dot product, essentially what you do is if you have a two-dimensional vector with x and y, the dot product, P and Q are two-dimensional vectors. The dot product is px times qx plus py times qy. Okay, that gives you the dot product of P and Q. Or if you want to look at it in matrix form, you've got P dot Q, right? So px times qx plus py times qy. So basically what you're doing is you're multiplying like terms, the x's together, the y's together, the z's together, et cetera, and then you're adding all of that together. So if you've got a three-dimensional vector P and a three-dimensional vector Q, the dot product is px times qx plus py times qy plus pz times qz. It's very simple to compute, okay? Another definition of P dot Q in terms of angles is the magnitude of P times the magnitude of Q times the cosine of some angle alpha. That can be derived from what is called the law of cosines, which if you took trig, you studied. If you're like me, you did that a long time ago and you've forgotten why that's true. We're just going to take it that it is true. I provide a link for you at the bottom of the page for you to go look it up if you want to look it up. Okay? Scroll down a little bit more and we get to why is the dot product important? Well, like I said, it gives you an indication of the angle between two vectors. So one very important result is that if P and Q are orthogonal to each other, if they are separated by 90 degrees, then the dot product is going to be 0. So let's look here. We've got a vector P that is 0, 4, 0. Vector P is vertical along the y-axis. So it's specified by 0, 4, 0. And we've got a vector Q, which is specified as 3, 0, 0. So the vector Q lines up with the x-axis, the vector P lines up with the y-axis. Because we know how axes work, we can immediately see that P and Q are at right angles to each other. Okay, there's a 90-degree angle between P and Q. So if what I told you just a moment ago is true, then the dot product of P and Q should be 0. Well, let's do the math. Set P at 0, 4, 0, set Q at 3, 0, 0, and multiply it out. px times qx, that's 0 times 3, plus py times qy, that's 4 times 0, plus pz times qz, that's 0 times 0, 0 times 3 plus 4 times 0 plus 0 times 0 gives you 0. Okay, it worked out as we would expect it would, because I told you that it's true. So essentially, if two vectors, in this case P and Q, if they are at right angles to each other, then the dot product of those two vectors will be 0. Okay? Any questions about that? Okay, let's scroll down to the top of the next page. If vectors P and Q are separated by less than 90 degrees, that's going to be true if and only if P dot Q is greater than 0. So if P dot Q is greater than 0, it means the angle between those two vectors is less than 90 degrees. So here we have a little diagram off to the side. It's hard to see, so that's why I have the little gray lines. P is, and I guess I should have moved the P a little closer to the arrow, but P there is in the YZ plane, okay? And Q is in the XZ plane. Now, they're not separated by 90 degrees. They're separated by alpha, and alpha is less than 90 degrees, okay? And if we multiply P, which is 0, comma 1, comma 5, and Q is 3, comma 0, comma 2, if we multiply those together, we'll see that we get a 10. And 10 is greater than 0, and that's a way for that dot product to tell you that the angle between them is less than 90 degrees. It's not giving you what the angle is. It's not computing the angle in this case. But what it is doing is it's telling you, hey, that angle has to be less than 90 degrees. And finally, if we scroll down a little bit more, if the angle that separates the two vectors is greater than 90 degrees, then P dot Q is going to be less than 0. So here I have P is minus 240, and Q is 300, and the angle there you can see is certainly greater than 90 degrees. If you do the multiplication, you get a -6. The dot product there is telling you, hey, they're separated by more than 90 degrees.
So
Okay.
it would be like maxed out whenever they are exactly opposite of each other. Is that true?
It'll, if, well, you can, I encourage you to play with these, but you will get a negative as long as the angle between the two vectors is greater than 90 degrees, and 180 is greater than 90. You'll see that you will get a negative number. Okay. So I think that's what you're asking. What if P pointed in exactly the opposite direction of X? You would still get a negative number. Okay. And again, why are we talking about this? Well, we'll see as we proceed with the course. But these dot products are used in lighting calculations. You need to know the cosine of the angle between the lighting source and the plane of a vector. You also need to know the angle between the a view vector, where a vector pointing towards the viewer's eyeball, and the incoming direction of light. So their dot product is used in vector calculations. It's also used, we'll see very shortly, next lecture, in determining whether or not a polygon is facing a viewer or facing away from a viewer. Okay, so it's very, very critical. We're about to start using it, and in fact, in our very next lecture, we will use it. The last operation that we wanted to talk about today was cross product. The cross product of two vectors returns another vector. Okay, so the dot product of two vectors returns a number, returns a scalar that gives us an indication of the angle between those vectors. The cross product of two vectors returns a new vector, and that new vector is perpendicular to the original vectors. Okay. This is a super critical operation because it allows us to figure out the orientation of a polygon in three-dimensional space. It allows us to get a surface normal for a polygon. So that's why we're considering it. It is, again, a critical part of determining whether or not a polygon is facing you or is facing away from you. Again, we'll see the details of that next time. But today, I just wanted to review what is a cross product. Well, a cross product is called a cross product because it is, you can think of it as defined by little x's, little crosses if you want to. So P cross Q, right? See that little vector that I have in the middle of the page there? Sorry, that little matrix I have in the middle of the page. Imagine the first row and the first column being marked out. And in that case, you would make a little X, a little cross between PY and QZ and QY and PZ. So what you would do is you will multiply PY times QZ, and then you'll subtract from that PZ times QY. So in your mind, you're making a little X there, a little cross, okay? That gives you the X component. To get the Y component, you mark off the first row and the middle column, and now you have PX times QZ, and you have PZ times QX, another little X that crosses those. Now, the way things work, there's kind of a plus minus mentality that goes on. So when you take PX times QZ, multiply those together, then you subtract PZ times QX. Well, we would also, after doing that, do a -1 multiplication of that quantity. And then the last value, the Z value, you mark off the top row and the rightmost column, and then you have PX times QY, and you have PY times QX, and that's another little X that we're doing there, a little cross. And so you take the PX times the QY, and you subtract from that the PY times the QZ. So right below there, you can see I have a +1 times PY times QZ minus PZ times QY. So that quantity, it doesn't change because it's times +1. And then the quantity PX times QZ minus PZ times QX, that quantity I multiplied by a -1. So that takes the sign and flips it. And then the last thing is PX times QY minus PY times QZ. And again, the result of that's multiplied by +1, so that doesn't change anything. If you do some math, you can see, well, keeping up with the minus of a minus is kind of confusing. So what we really do normally is we just swap the order. So instead of PX times QZ minus PZ times QX, and then put a minus on that, we flip them. So it becomes PZ times QX minus PX times QZ. So if you flip the order there, you get the same result. So anyway, that's how you compute a cross product. And what does that give you? That gives you a vector where that vector is normal, is orthogonal to the two vectors. So here's an example at the top of the next page. I've got a vector P that's 405, and I've got a vector Q that is 302. As you can see from the little dotted lines, both of those vectors are in the XZ plane. If I do a cross product on those two vectors, I get the vector N, which is 070. If I do the math, see that at the top there, it gives me 070. And if I normalize that, I get 010, which is exactly what you would expect since P and Q are in the XZ plane. The vector that is at 90 degrees to that has to be a vector that points in the direction of the y-axis. And once I normalize it, it's just to a length of 1, it's just 0, 1, 0. And that, my friends, gets us all the background we need so that next time we'll be able to start on backface culling. So that's all I had for you today. Are there any questions?
So I've just kind of been thinking about this as we've been going through it. The cross product gives you a normal vector. If I remember right.
That's correct. Yes.
So if we're defining our polygons as triangles, if you were to just choose one of the vertices and move that to the origin, you'd have two vectors that you could.
Well, everything you think, it's good that you're thinking in this direction because this is the topic of Wednesday's lecture, where I'm going to show you how to use cross product and dot product to be able to determine whether or not a polygon is visible from the viewpoint, whether it faces towards or faces away. And we're going to have to do a couple of things. We're going to figure out the orientation of the polygon in three-dimensional space. That's going to require a cross product. And then we're going to have to figure out what's the angle between the viewer and or a vector that points towards the viewer and the orientation of that polygon. And that's going to be a dot product. So cross product and dot product working together are going to allow us to do polygon visibility determination, which is the heart of backface culling.
Cool.
Any other questions? Okay, gang. Well, thank you for sticking with me on this snowy day, and I'll see you guys on Wednesday. Okay. I'll talk to you later. Bye-bye.